In case the online folks didn't hear, because forgot to unmute because it automatically mutes us. We were just talking about the challenge ladder game for in-person people, so you didn't miss anything.
Okay, can people hear me all right? Can people online hear me?
Yes.
Okay, great. I'm hearing yes. So, okay. My name is Will Barnes. I am a research scientist at NASA Goddard. I'm also one of the lead developers of the SunPy project that Nabil talked about on Monday. So what this session is going to be is sort of using a lot of the pieces that Nabil presented on Monday, and some of the pieces that Jim presented in his PySpeedas tutorial on Tuesday to study a single event starting from the sun all the way to the Earth. And I'm going to kind of give more the solar remote sensing side, and then Jim is going to take over and kind of show the more in situ PySpeedas side of things. So, okay, so we're going to go, just to start off with, I'm going to go to the summer school repository. I'm going to go to the SunPy tutorial folder, and I'm going to go to the SunPy PySpeedas folder here. This is the same folder that the SunPy tutorial was in, but just a different subdirectory. I'm actually going to minimize this. Okay, all right. So, like I said, we're going to start with an event that was that coincided with, or that hit Earth around the 24th of March, 2023, and we're going to kind of start looking at that event on the sun and kind of move Earthward. Also, if there's any questions during all this, just raise your hand. I'm happy to do questions as we go. Okay, so annoyingly, the first thing is that when Nabil and I were preparing for the summer school, there were some last-minute bug fixes that didn't make it into the environment that's already built here. So the first line is to do a pip install of the latest version of SunPy in this other package called SunPy Soar that I'll explain more in a second. But this line should be pretty short because it's just doing an upgrade to just 2 packages. We don't need to talk about why this, but this should be pretty quick. This is already finished, and I'm just going to minimize all of this here. Okay. Most of the imports I'm going to kind of do as we go, just to show what parts of which package I'm using, but I'm just going to do a few standard imports of matplotlib, numpy, and then astropy units, which Nabil talked about on Monday, which provides these kind of unit-full computations. And then a few other things that I'll explain as we go. We are going to download a decent amount of data as part of this notebook, if for whatever reason, because we're all going to be downloading this data all at once, if you're following along, that there are any network issues you have. If you're running on HelioCloud, there is a set of all the data for this notebook in the Scratch space, and to get that to work, all you have to do is uncomment this line. But we're going to try to do this actually downloading the data. Okay. So in the course of this notebook, we're going to study this event, this 24 March 2023 event. That was a CME that erupted off of the solar disk that was associated with a flare that happened on the solar disk. And to kind of in the course of doing this, we're going to learn a couple of things. We're going to learn how to search for and download both in situ and remote sensing data, so images with SunPy. We're going to learn how to create, manipulate, and visualize time series data using the time series objects in SunPy. And then we're going to also create some movies from a sequence of SunPy map objects. Additionally, and this is going to be covered more by Jim is that we're going to search for and download some in situ data with PySpeedas and also do some visualization with PyTplot and X-ray as well. All right, so the first thing is, when did the CME happen? And we know, okay, it happened, it arrived at Earth around 24 March 2023. And so, we can sort of estimate that it left the sun around 3 to 4 days prior. Say we can make a rough estimate of when that time interval was. And so to take a look at this eruption of the CME on the solar disk, we're going to use the LASP instrument, which is a coronagraph that's on the SOHO spacecraft. And to do this, we're going to search for data using FIDO, which is the search interface that Nabil showed off on Monday. So it's the primary interface for searching for data with SunPy that allows you to search across lots of different data providers. So we're first going to start off by defining this time interval using the AstroPy time objects that we talked about yesterday morning during Bob's session, the first part of the session on time. Because everything in SunPy that has to do with time is expressed as an AstroPy time object. So all the time, whether it's search or as I'll show later, it's truncating a time series, anything to do with time expressed as an AstroPy time object. So we'll declare the start of our event on the sun and the end, and then I'll do a FIDO. I'm going to import the FIDO client and the associated search attributes, and I'm going to run this search. And what I'm doing is I'm using this time interval starting on the 20th of March at 1 and going till the 20th of March at 7. I'm looking for the LASP instrument, and I'm actually going to choose a particular detector on the LASP instrument. This is the C2 detector, which is the smaller inner field of view. You'll see this in a second. Okay. And because actually this data is relatively low cadence, I'm just gonna download every single LASP file in this relatively large interval. And so, okay, this is kicking off my data download, and wow, that was actually shockingly fast. So we just downloaded 38 LASP files. These are packaged as FITS files, which Nabil talked about on Monday. And so I have my FITS files, I have them on disk. Now I'm going to load these into a SunPy map object. And so as Nabil showed on Monday, you can pass a FITS file or a path to a FITS file straight into a SunPy map, and it will create a map object for you. What you can also do is you can pass in a directory of maps and pass the sequence equals true keyword, and it will return to you this object called the map sequence, which essentially you can think of as just a stack of maps, in this case as a function of time. And what this is particularly useful for is building animations, which is what we'll do in a second. The first thing I'm going to do, though, is I'm going to divide each map by the exposure time. So on most, essentially all imaging instruments, the shutter is open for some period of time to allow photons to hit the detector. And oftentimes we want to normalize that quantity out. And what map allows you to do is this handy thing where I can have a map object. So this is not just an array, it's an array plus all of the metadata. And I can actually do arithmetic operations on that map object. So what I'm doing here is I'm building up a new list. And for each member of that list, I'm dividing it by the exposure time that's a property on the map object. So actually, if I go here and I just look at map.exposure time, why isn't this auto-completing for me? Oh, because map is, so if I look at one of these maps in my stack and I do the exposure time, I can see this is a quantity that it returns me. And what I'm doing here in this kind of complicated line below is I'm taking each one of these maps, in this case I'll just do one, and I'm dividing it by that exposure time. And what you can see once this prints out is that this is just returning to me the HTML rendered view, is that it returns to me a new map, and now the units on this new map are in oh, this is not going to work. These have 1/seconds because I guess there's not a unit on the. So if these maps were in units of counts or dn, you would see a dn over seconds. But more importantly, we're normalizing out the exposure time for each one of these maps, and then we can do this without having to pull out the data array individually from the map. We can just do that arithmetic operation straight on the map object itself. Okay, so now we have another map sequence. I'm just creating another map sequence again. And if I take one of those, if I just look at one of those members of that sequence, I get the map at a particular time here. And so I don't know if you can see it on the screen so well, but if you're looking on your screen, you can sort of see some structure around the outside of the disk. So this big black blob in the center is the occulter of the chronograph. It's blocking the light of the solar disk to enhance the kind of off-limb emission you're seeing. And then there's some sort of defects off here to the side. These are actually uncalibrated LASCO images. But for our purposes, we actually don't care because we're just looking to see. We just want to see what the structure is of the CME as it comes off the disk. So what we're going to do, because these structures appear relatively faint here, is we're going to do a running difference from this stack of images. So again, what I'm going to do is I'm going to recreate another map sequence. I'm going to loop through kind of two lists here. I'm doing the kind of the n+1 map and the nth map. And then I'm just going to subtract those two. And again, because map allows you to do these arithmetic operations, I can just subtract this. We have a property on each of these map objects that is what we call quantity. And what this just returns is the array, but in a unit full with units attached to it. So if I just looked at .data, for example, this would just return to me the NumPy array. If I look at .quantity, this returns to me the array with units attached to it. And so I'm subtracting the previous array from the current map, so that I can all I care about is the changes from one time step to the other to create what we would usually call a running difference. Okay, so I've got my new map sequence that's now a running difference. And I'm going to create an animation from this. And Nabil showed a little bit of this on Monday. But when you call .plot on these map sequence objects, instead of returning to just a plot, it returns to you this animation object. And what we're going to do then is we're going to animate this within the notebook. And you'll see what this looks like in just a second. If this renders. Okay, great. Okay, so now we've got our little animation, and I can play it. So what you'll see here is the CME erupt off the limb of the disk as viewed by LASCO. And again, this is a running difference, so all it's showing is a difference from one time step to the other. But it provides a really nice way to just visualize this eruption off the disk. Okay, all right. So we have one kind of view of what this eruption looked like, and now we know about when this happened. That this kicked off around 1400 or so on the 20th of March. So let's now use PySpeedas to look at a few in situ observations from also from SOHO. So the SOHO spacecraft has a whole suite of instruments. One of the remote sensing ones is LASCO that we just looked at, but there are also a few in situ ones as well that I don't know very much about. So if you want to know more about this, I would talk to Jim or any of the other people here who are much more well versed in sort of in situ measurements. So we're going to look at data from the Celius instrument, and using PySpeedas, we can pass in a time range, and we're going to use just the same event start and event end times that we had before. Because PySpeedas doesn't work with AstroPy time objects, we can just pass in the strings for those times. But luckily, using AstroPy time, it's easy enough to just use the string format using this .iso. And so, for example, that will return, if I do a time event start.iso, this just returns me this time string. We're also going to extend the end of our interval here by about 4 days to account for the time it takes the CME to propagate to the spacecraft, because SOHO is much closer to Earth. Okay, and then we can do as Bob showed yesterday, we can do arithmetic on these AstroPy time objects. So I can literally add 4 days using an AstroPy quantity, and that gives me back a new time string. And then again, I can just call the string formatted version of that. Okay, so we've downloaded our data, and then we're going to do the same thing for the ERNIE instrument also on SOHO. So these are just 2 different remote sensing instruments. So now that I have my data, I've downloaded it. I can use PyTplot to visualize this data. I'm just setting a few different options to build this plot. And then when you actually build the plot, you get back these nice stack plots of these 3 different quantities: the proton velocity, the proton density, the other proton velocity quantities that I'll probably let Jim talk more about. And then we can see, about, if we go down here and look at the time axis, March 24th, about 4 days later, we see this enhancement especially in the proton density. Okay, so now we've used SunPy to look at remote sensing observations. We've kind of figured out, okay, when did this eruption happen on the disk by looking at LASCO, and we've seen that we can see it in the remote sensing data from the same spacecraft, about 4 days later. Okay, so now we've seen the eruption. What we now care about is looking at the flare that preceded that eruption. And the first thing we're going to do is we're going to look at the GOES XRS data. So the GOES series of satellites has a soft X-ray irradiance instrument that just takes disk-integrated soft X-ray time series data. And it's often really useful for seeing when a flare starts and when the peak time of a flare is and its duration. So again, we're going to go back to FIDO. We're going to use FIDO to search for this GOES data. And I believe Nabil showed an example of doing something very similar on Monday. So we're going to use, again, our same time interval that we started out with. We're going to choose the XRS instrument on GOES. We're actually going to pick a particular satellite number because GOES is a whole series of spacecraft, and there are times where 2 satellites, like the observing kind of lifetime of the 2 satellites overlaps, but we only care about getting it from 1. So we're going to choose one particular spacecraft, and then we're going to get this time resolution of 1 second data. Okay, so let's run that, and then we're going to we can look and see, okay, what did this return? And we see we get back one file, which is what's expected. GOES delivers 1 per spacecraft, 1 file per day. And again, then we can go and download this data, which is pretty quick. It's just one fairly small file. Okay, so similar to the way MAP works, we're going to just pass in this file that we've downloaded that contains all of our GOES time series data. This is a netcdf file, but it doesn't really matter because doesn't really matter what it is in this case, because we're just going to pass it in and we're going to let time series do all of the parsing for us and pull in the metadata and the data associated with that. The reason I'm passing this concatenated equals true keyword argument here is that in some cases, if I was extending this search interval over a few days and I got back multiple files from GOES, without passing this in, if I just passed in a series of a list of netcdf files, I would get back multiple time series objects. But what this concatenate equals true keyword does is it tells it, okay, if I get multiple time series objects back, stitch them all together into a single time series and handle especially sort of bridging like the metadata, for example, from one day to the next. In this case, it actually doesn't matter because we only have one file. So okay, then I'm going to just call up this peak operation on here, and I can just get sort of a quick look of what this time series actually looks like. And you'll notice, okay, this extends over kind of starting early on March 20th, really for the entire day of March 20th up till midnight, which is why this says March 21st here at the end. And again, this is a consequence of the fact that Go's data is packaged as one file per day. But we're only interested in a relatively small kind of subset of this data. And so what we're going to do is we're going to use this truncate method on time series to truncate to only the portion of the data, this data that we care about, which is defined, again, by the same interval that we defined right off the bat, which is just a 6-hour interval on the 20th. And so what I can do is I can use this truncate method. And the first thing I do is build a time range using the start of the event and the end of the event. And this truncate method will just give me back another time series. So if I go and do TS, goes flare dot peak here, and I have to close my parentheses. I can see that I get back another time series object, but now we're only going from 1300 to 1900 on the day we're looking for. This is not the most helpful visualization. So what I can do is I can only pull out actually the XRS B, which is the longer wavelength soft X-ray curve, and I can use these two helper functions from AstroPy for easily visualizing both unitful arrays and also time objects. So these things are called context managers. I'll talk a little bit more about those later. But this is just all this is to say is that what these give you are support for easily labeling plots appropriately if you're plotting a time object or a unitful quantity object. And so you'll notice that I get back a nice unit label here. I get back these nicely formatted time strings here, and I didn't have to do any of that explicitly. That's just given to me by these two context managers. Okay, and so this is the soft X-ray emission as observed by GOES for the particular time range we're interested in. And so now we can see, okay, the flare on disk starts a bit before 1400 on the 20th. It reaches its peak time a bit before 1600, and then has decayed pretty sufficiently by the end of this range that we've showed up to 1900. You see, there's a very sort of classic shape of the impulsive rise of the flare, and then the kind of much longer decay phase. Okay, and so let's use this curve to then define, okay, what's the peak time of our flare? And all I'm doing is using this argmax function, which just tells me what is the index of the array at the maximum value for that array. And then I'm using that and passing it into the time object, so I get the time at which this quantity is maximum. So what is this time around here? And as expected, this is around 1529. Okay, I'm just going to pause here before I go on and see if there are any questions or people. Yes. Oh, yeah, thanks.
So the reason you chose to show us the truncate part was because when you're loading the data, it had event start and event end, but the file that contained that time period was like a whole day or something?
That's correct.
Okay.
Yeah, which I appreciate is kind of confusing because you're doing the search and then you get back a result that is a much wider interval than the search. But what it'll do is it'll say, like for example, if this time interval stretched all the way to the 21st, if it included any part of the 21st, it would give me back 2 files, 2 days worth of data. And then it would be up to me to sort of truncate to that particular time series. But it's a consequence of the way the GOES data delivers it. It's like they only deliver data at a resolution of a day. And so you always will get back a day's worth of data. Yeah. Okay. Yes.
sorry, this is going to be a syntax question. So I think it might be back in line 30. I don't know the exact line number where we define Q underscore goes.
Yes.
For our query.
Yep. Yes.
So in line 29 here, you just print Q goes and there it lists, what if I wanted to see, for example, all of the different, in this case, I know you selected satellite number 18. But what if I wanted to specifically go and see all of the different satellite numbers? What is the syntax to doing that?
I would just exclude, if I just exclude specifically searching for the satellite number, it will return to me two results. So these are the ones, oh, sorry, yeah, go ahead.
But then I just say, I just want to look at the satellite number, not the whole list here.
Oh, like you mean from the table here?
Yeah.
Oh, yes. So, okay. The return, when you do a FIDO query, it will return to you as many results as there are providers. So in this case, I'm getting back data from only one provider. I'll show some examples of where you get back more. So it's a list of length equal 1 because I only have one provider. And then this is just a table. So then I can select out.
You could just type satellite. Okay.
Right. Yes.
I was missing the 0 there.
It's not the most.
Okay.
When you know why, it makes sense, but it's not the most intuitive thing to be like, why is this thing a list of like length equal 1? But it's because with FIDO, you can get back an arbitrary number of results per search, depending on how complex your query is.
Okay.
Yeah. So this is just a table, and then you can index it just like you would any sort of like pandas data frame.
Okay. All right. Thank you very much.
Yep. Okay. All right. I will go ahead and move on then, but please, again, feel free to interrupt if there are any other questions. Okay, great. So we know when this event occurred based on our GOES data. So now we want to see, okay, where on the solar disk did this happen? And to answer that, we need remote sensing observations of the solar disk. So not just disk integrated stuff, not just LASCO, but stuff that actually sees the disk. So the first thing we're going to say is, okay, well, what instruments can we use to do this? And we're going to Nabil mentioned this in his talk on Monday, but we're going to use the Solar Mock project or package, which is a SunPy affiliated package, to sort of look and see what instruments what instruments do we have and where were they when this event occurred. So I'm going to define a couple spacecraft here, SDO, which has AIA and HMI on it, Parker Solar Probe, Solar Orbiter, and then SOHO, which included LASCO and the kind of suite of in situ instruments that I showed earlier. Okay, so to do this, I create this solar mock object. I'm going to pass in the peak time that I defined using my GOES soft X-ray curve above. I'm going to pass in this list of spacecraft, and then for reasons I'll show in a second, solar mock also wants you to pass a list of solar wind velocities for each one of these spacecraft. But the main takeaway is what this allows us to do is this allows us to visualize where these different spacecraft were at a particular time. And then here I'm showing the connectivity using the Parker spiral to each one of these spacecraft. So the sun is at the center, and then these boxes show the individual spacecraft. So Solar Orbiter is shown in light blue here. SOHO and SDO are kind of on top of each other in this plot. This still makes the point that they're at about the same vantage point. And then Parker Solar Probe is really, really close in, all the way over here to the side. And so these relative positions are going to come into play in just a second when we start looking at the data from these different spacecraft. So we've already looked at data from SOHO. That's what LASCO was. So we're going to look at some images from SDO and also from the UV imager on Solar Orbiter, and then at the very end from Parker Solar Probe as well. Okay, so what the takeaway here really is that both this CME was approximately Earth directed here. So both SOHO and SDO will see it almost head on, and then we'll have also a view from Solar Orbiter too. Okay, so the first thing we're going to do is that we want to make sure that Solar Orbiter and GOES, we're seeing the same flare. We don't really know where this is on the disk yet, so we want to make sure that they're seeing the same thing. And so to do this, we're going to look at time series data first from from the STIX instrument, which is a hard X-ray instrument on Solar Orbiter. What I'm doing here is I'm using this package called STIXPy, which is a package built specifically for searching for and loading STIX data. And it's actually not currently a SunPy affiliated package, but it uses all of the same infrastructure. It will be in the future, but it uses all the same sort of tools as SunPy does. And notably, one of the main things it does is it tells Fido how to search for STIX data. So here I'm doing an import from STIXPy. I'm importing the STIX client. And so what this is kind of doing underneath the hood is that it's then telling Fido that it now can go search the STIX data center for STIX data. So before, I wasn't able to do that. Now, by importing the STIX client, I'm able to search for STIX data, again, using the same Fido interface. And so there's kind of a little bit of magic happening underneath the hood. But what I want the sort of takeaway to be is that you can extend Fido to search for additional pieces of data without actually modifying anything in SunPy. You can register new clients, tell Fido how to search them in an external package. And I'll show one more example of this before we end. Okay, so I'm going to search for the STIX data again over the same interval, and then I get back one result again from my STIX client. And these are just kind of quick look data, but that's all we kind of need for the purposes of this demo. I'm going to do the same kind of set of steps as I did before. I'm querying. I'm going to download. I can see the result. I download the data to a particular file. And then as with the XRS data, I'm going to create a time series. And so again, what I'm doing here by importing this quick look functionality, I'm telling time series how to parse STIX data. So just like similar to the way Fido works, I don't actually need to modify anything in SunPy in order to tell time series how to parse a new data set. So the SunPy package by default doesn't know anything about STIX data, doesn't know how to parse it. But by using this external package, I can tell time series how to do that. And then I can use the same interface as I did before. And so if I do a quick peek, I can see, okay, this is the STIX data over a wider time interval than the one we're looking for, similar to what we saw with GOES. And then what we're going to do again is truncate down this time series to just look at the part of the event that we're interested in. And so there's a lot of plotting code here. It's not particularly important to understand exactly all the stuff that's going on. But all I'm doing, I'm happy to answer more questions about it later, but all I'm doing is plotting the STIX light curves on top of the GOES light curve that we saw earlier. So again, GOES here is shown in red and is on the right axis here. And then the two STIX light curves, this is the lower energy one in blue and the higher energy one shown in orange are overplotted here. And so what I want to point out is that there's clearly some sort of correlation between these two. But if you look at this peak right here where you can see my cursor, there's some offset between that you can really see in this tiny little blip here, and you can see it kind of in the subsequent smaller peaks farther down. And so, okay, why is this, right? We have these two things that are clearly look like they're seeing the same event, but there's some offset between them. And the reason for that is light travel time. So if we go back up here and look at our plot of the spacecraft positions, Solar Orbiter is much further in much closer to the sun than so GOES is approximately at Earth because it's a geostationary satellite. And so the photons are hitting the STIX detector way before they're hitting the GOES detector. But we can correct for that, thankfully. And so, okay, what I can do to do this is that I can query the position of Earth at the start of our event time, and then I can go and grab the position of solar orbiter also at the start time. And I'm using, there's a function in SunPy, provided by SunPy coordinates, to get the position of Earth at any given time. And I'm going to use this function called get horizons chord, which queries the service called JPL horizons that returns to me the spacecraft position at any given time. And what both of these return here, as I'll show right here, are these rich sky chord objects, right? So this tells me in heliographic Stonyhurst, which is, you can think of as just a spherical coordinate system centered on the sun, roughly speaking, where 0 degrees longitude is just the sun-Earth line. And this tells me the position of Earth at a given time, and then I get the same return type for the solar orbiter location. Okay, so now I have my lawn lat radius at a given time for the two. What I'm going to do to approximate the light travel time is just say what's the difference in the radii between the two, and then divide by the speed of light. And so I'm using, again, all the same, because these two radii are quantity objects. I can subtract the two to get a radii. I can use the astropy constant for the speed of light. I can divide by that, and then what I get back is this light travel time, and I'll just print this here. And this is in seconds. So I get about 240 seconds of difference in light travel time between the two spacecraft. And so what I'm then going to do is I'm going to do all the same plotting code, but the only difference is here is I'm subtracting off the light travel time from the GOES time here. And because these are rich time objects, I can just subtract this unit full light travel time that I just calculated, and I get back another time object, but this time adjusted. And when I overplot these, what you can then see is that the two peaks then line up. And so these are well correlated, and now I've adjusted for this less light travel time here. And so, okay, from this we can conclude that both GOES and as a result, SOHO, SDO, and Solar Orbiter are observing the same event. Okay, so let's finally go and look at some UV images of the sun. We've looked at enough time series so far. Okay, so again, we're going to construct a FIDO query, and this time we're going to look for data from AIA in the 304 wavelength bandpass. And so 304 primarily observes a particular atomic transition of helium-2 is the dominant thing that emits in that bandpass. And what it's seeing is primarily the solar chromosphere. So it's like the lower layer below the corona. What we're also going to do is we're going to look at data from the EUV imager called EUI on Solar Orbiter. And so EUI also includes a channel that's a similar bandpass as the 304 channel on SDO. It's approximately the same. And so what I'm doing here is I'm doing the same thing as I did with my STIX data before, is I'm importing this thing called SunPy SOAR. And the SOAR is the Solar Orbiter Archive. And so by default, out of the box, SunPy doesn't know how to search the SOAR for solar orbiter data. But what this SunPy SOAR package does is it tells FIDO how to do that search. And so now I can define this search for using these SOAR product names, which is something specific to how you look for data on the Solar Orbiter Archive. These are a bit they're not the most intuitive, but this is how you search for data. And what I'm doing here is I'm looking for data in the 174 bandpass, which is going to show me the kind of hotter coronal material, and then I'm looking for images from 304, which is that lower temperature chromospheric images, because they show me the lower atmosphere of the sun. Okay, so I've built up this kind of complex query now, where I've said in the case of AIA, I want data from AIA, and I want it in the 304 bandpass. In the case of the Solar Orbiter Archive, I have to search for data a little bit differently, but I can still do this all through the same interface. I can say I want data level 2 data only, which is at a certain processing level, and then I want either 174 images or 304 images. And so what I'm going to do is I'm going to pass all of these queries into FIDO here, And what I should get back now is 3 results. I get 1 for AIA, so you can see I get data from 3 providers. I get 1 from AIA from the Virtual Solar Observatory, or the VSO. I get another one from the Solar Orbiter Archive, which is returning to me these 174 images. I get 72 images back. And then I get a third one for the 304 images. Okay. So now this is the part that where my demo might fall over, because I'm going to download a lot of data. So I'm going to pass all these queries back in and call Fido fetch to download these. And I'm just going to do this here as I explain what's actually happening. So I'm downloading all of the AIA data. And the reason I've kind of pulled apart this query here is that I only want to download every other image from one Solar Orbiter UI for the 174 and the 304 band passes. And that's just to reduce the amount of data that I'm downloading here. If instead you passed in just this Q EUV object, it would just download all the data. But I'm just halving that. So you can treat these response objects just like you can index them in the same way that you would any sort of data frame if you wanted to avoid, say, downloading all the data that you searched for. So you're not limited to what's in your return query. You can kind of pare that down as needed. Okay, and this is proceeding much faster and much more smoothly than I anticipated. Great. Okay, so we just downloaded 73 images, 36 from one channel, the 174 channel of EUI, 36 from the 304 channel of EUI, and then 1 from AIA. Okay, let's make our AIA map really quick. And here I'm just passing in a single FITS file. And then I'm going to do something first is I'm going to use this AIA Pi package, which is a SunPy affiliated package specifically for doing analysis of AIA images. And I'm going to correct for the degradation of this image. So the 304 channel in particular on AIA is quite degraded. AIA launched about 14 years ago. And there's sort of there's been a lot of effort to understand how the instrument has degraded as a function of time. Most of the channels are okay. The 304 channel is the most degraded, but you can do some things to correct for that. And so what this does is just applies a scalar correction factor to enhance the brightness of the 304 channel. So I can take a look at this image, and this is what the 304 image looks like as observed by AIA. And you can see this really bright kind of what this is called a flare ribbon structure here, kind of in the top left quadrant. And that's the thing we're going to be interested in. So we can kind of visually inspect this and say, okay, I want to crop my image. This is where I think the flare is going off. I'm going to crop my image to this region here. And so to do this, we can use these SkyChord objects that Nabil touched on Monday, and then Bob talked a little bit about yesterday. And we can define the kind of bounding box for our image in world coordinates. So I can look at the image here. This is exactly what I did when I made this tutorial. Is I said, okay, I want to kind of by eye, I want to look at this image, and I see that okay, the kind of the ideal bounding box, that the bottom left corner starts at about around 500 550 arc seconds. So starting like about here, and then in my helioprojective x coordinate, and then my my y coordinate was at about 300 arc seconds. And so what I can do is I can create a SkyChord that says, okay, that's the bottom left corner of the bounding box I want to crop to. And then I'm going to say the width is about 500 arc seconds and the height is about 400 arc seconds. Okay, so when I do that, I can pass those things into this submap command or method that's on my map. And then when I visualize that, you can see, okay, so on the left here is my original image, and I've just drawn a box over the thing that I cropped. Again, using the exact same way to specify that bounding box. And then I'm plotting here on the right my cropped image. Okay, so we can see this. We have this sort of nice, very characteristic flare ribbon structure that the 304 channel shows very nicely. Okay, yes. Do you have a mic? I don't have a microphone close to me. Thanks.
So does MAIA, does that carry all of its like matplotlib axes with it in the object itself? Is that how you're able to call all these plotting functions on it, or how does that work?
So the plot method is what creates the axis itself, or it knows how to create the axis. So underneath the hood, so this is all done using matplotlib. Underneath the hood, we're using something called WCS axes, which is a part of AstroPy. And so what that does is it creates a matplotlib projection, which is a functionality provided by matplotlib using the WCS which is the world coordinate system that allows you to translate between pixel and world coordinates. And so actually this command here, if I actually returned something from it, if I did this, when I pass in this projection equals keyword, that's what creates the axes, the coordinate-aware axes that I'm plotting on top of. And it's actually, what's really happening is that it's pulling out the WCS here, so this does the same thing. And if you look at the return type of this AX object, this is this WCS axes thing, and that's where all like the magic happens, basically. So what all really the map does, there's some kind of stuff that happens in plot, but the real magic is passing in the WCS to create this WCS axes thing. So I'm happy to talk more about that. You get into the weeds really quickly, but there's a lot of like really cool stuff that allows you to do. It's very complicated, but it's really awesome. Yeah.
Thank you.
Okay. All right, so I have loaded my AIA image. Now what I want to do is I want to load in my solar orbiter images. And so I'm going to create a list of maps, both for the 174 image and the 174 channel and the 304 channel. And so this is loading 72 individual maps or 36 maps for 174, 36 for 304 into their own list. And if I just take a look at one of those, this is the 304 channel as observed by EY on solar orbiter. So this is the full sun imager. There's actually two imagers on EY. There's a full sun imager and there's a high resolution imager. This is the full sun one. It's designed for seeing kind of off-limb stuff often. But I'm zoomed really far out here, right? And so what I want to do is you can kind of see this, again, this same structure that AIA is observing. And you can kind of see it's in a slightly different position because of the different spacecraft position here. What I want to do is I want to zoom in on that structure since I'm kind of a wide field of view. And so what I'm going to do is I'm going to take the bounding box that's defined by the coordinates or the corner coordinates of this zoomed in image here. So this is the coordinate here and the coordinate here. And I can access those just using these bottom left and top right chord. And so if I just print these, just one of these, you can see again, this is the same sky chord object. Now I'm in this projected frame of my image. What I'm going to do now is that there's some kind of magic that happens here is I'm going to crop each of the images in each of the maps in my stack of UI images to a field of view that's defined by my AIA field of view. Because these are coordinate-aware objects, they know what coordinate system they're in, and they know how to translate from one coordinate system to another. I can do this directly. And so what I'm going to do is I'm going to loop over each one of my maps. I'm going to transform the bottom left and top right coordinates to the coordinate frame of my UI image. And then I'm going to pass that in again to the submap. And I'm just going to create a new list of zoomed in 304 submaps. The kind of magic part here is that I'm using this this context manager called Propagate with Solar Surface. And I can talk a lot more about that if anyone wants to. But what it's basically doing is it's telling the coordinates transformation machinery that to track the or to include the rotation of the sun as it's doing those coordinate transformations. So what it's effectively doing is it's tracking the active region, the bounding box that I'm defining here with the bottom left and top right as the sun rotates, according to some model for differential rotation. Okay, so I'm going to do that. I'm going to crop each one of those, and then I'm just going to create a new map sequence here because we're going to animate these as well. And so then what I'm going to do is I'm just going to apply this same set of steps to our 174 maps. I'm just doing it in a slightly more condensed format. But again, I'm cropping while accounting for the rotation of the sun according to the bounding box that I defined above. Okay. So now what I'm going to do is similar to what I did with my LASCO maps. I'm going to make an animation using these map sequence objects that I did before. And now what we should get back is a movie of the flare ribbon as observed by UI. So I'm going to just play this. And so what you can see is the flare ribbon brightening and expanding as the flare goes off. And you start to see kind of maybe these faint post-flare arcades form overhead. And this is just, I'll let this play a few times. So I think this is really cool. And what you'll notice is that the coordinate grid here is moving like as the movie plays. And so that is a consequence of, for one, the plot knowing, or the plot axes knowing about the coordinate frame that I'm in. And also it's moving because my field of view is moving to track the active region as it rotates. Okay, and I'm going to do now the same thing with UI 174. And I'm just going to show this same movie. Okay, so this is, again, the same active region, same time steps, but observed in a slightly higher temperature. So again, we're seeing the same flare go off. What you'll see here is that you don't see as much of the foot points brightening here. What you do see a lot of is these hotter post-flare loops that form right after the flare goes off. So we're seeing kind of different, by looking at different wavelengths, right, we're seeing different parts of the solar atmosphere in different temperatures. Okay. I'm going to go a bit quickly here because I'm very short on time, but what I'm going to do here is that I'm just going to take all those images, and I'm going to collapse my 304 and 174 images over the spatial dimensions. I'm going to create time series out of them. And then what I'm going to do is I'm going to take the sticks data and basically do the same thing. It's already as a time series, but I'm going to do some things to account for the exposure time and do some background subtraction. And what I'm going to do is I'm going to take all of those and I'm going to interpolate them into a common time grid, and I'm going to build up a time series object from all three of those time series. And so what I have now is a time series object that includes three different quantities from Solar Orbiter, the averaged 174 emission, average 304 emission, and the sticks 4 to 10 kV. And then if I plot all these three, and again, the same way, using all the same sort of time series machinery, I can see blue shows the sticks data, and then orange green shows the sticks data, orange is the UI 304, and then blue is UI 174. And what you can kind of see here is that my sticks data peaks first, my 304 light curve peaks second, and then lastly, my 174 light curve peaks. And this is just, again, emphasizing this point that we're observing the same event with all three of these instruments. So what I'm going to do to kind of quantify that is I'm going to calculate a cross correlation between these two. And there's some functionality for doing cross correlations, especially in higher dimensions, but this works for time series as well, in this package called SunKit Image, which is another SunPy affiliated package. And so what I'm doing here is I'm calculating a cross correlation between pairs of all of these time series data. And so what I'm going to do is then plot those cross correlation curves as a function of time offset between them. And this is what this final plot is. So blue shows the cross correlation between the STIX data and the 304 channel. And green shows between STIX and 174, between 304 and 174, and then orange is STIX and 174. And so the main point I just want to make is that you see the shortest delay between STIX and the 304 data because you see the brightening in the hard X-ray and then the 304 emission when the foot points light up, as opposed to the much longer delay between the 174 where you see those really bright loops and then the STIX data, which happens first. Okay, I'm going to actually skip the in situ bit of this, and I'll let Jim talk about that mostly. What I want, the final plot that I want to show is just, and I'll kind of blow through this relatively quickly, is data from WHISPER. So WHISPER is a white light imager on Parker Solar Probe. And what it does is it looks out the side of the spacecraft. So there's the heat shield on the front, it's looking to the side. And because of the position of Parker Solar Probe at the time of the event, by looking out the side, we're seeing the CME as it goes past in white light. And so if I download all these data, which again is impressively fast on HelioCloud, I can again do the same trick, create a map sequence of the two. With WHISPER, there's actually two different cameras with two different projections. So this is what I'm showing here. There's an inner camera and an outer camera. So the inner, as you might expect, shows closer to the sun. The outer camera is looking farther out into the heliosphere. And from what you can probably tell from these kind of funky grid lines is that the projections of these images are quite odd, in that they're not very aligned with the pixel grid, right? But that's okay because our coordinate machinery understands all of that. And in particular, one of the really nice things you can do using this whole coordinate stack is doing reprojection to common coordinate frames. And so there's a lot of details going on in here. What we're just going to focus on is the output. So what I'm going to do is I'm going to map these two cameras at each timestamp to the same pixel grid. So I'm going to combine the two images using a reprojection. So this is the output that you get when this is just at a single timestamp. So this is the sun over here. This is the inner camera as the CME is starting to lift off the limb, and this is the outer camera. And then again, if I do this whole procedure for each one of my timestamps that I've queried, and then I do similar to what I did with the LASCO data, if I take a difference image, I can see the difference. I can see the structure of the CME as it erupts off the limb. And so this takes a little bit to do because it's doing the reprojection for each time step. It's taking the running difference, it's building the animation, and then it's playing the movie. So okay, here is the final plot. So I will just play this. If it finishes, okay, great, yes. All right. So here is the data from WHISPER. So you can see it lift off in the inner camera as the CME goes off here, and then as it propagates farther out into the heliosphere, you see it in the outer camera as well. And again, you can kind of see how the shapes of these two arrays are deformed when I reproject them onto this final combined pixel grid here. So okay, that's sort of the end of the part that I want to show. But in kind of, in summary, we looked at all these remote sensing data, some in situ data with both our map and our time series objects. And because we have a sort of a single data model, mainly map and then time series for time series data, it allows us to work with all of these different data sets together in kind of a seamless fashion is the kind of point I wanted to make. And then similarly for doing data search, Fido also allows you to do that. So I think now Jim is going to show some stuff from PySpeedas for this same exact event.
Is there a similar function also to combine solo high tiles?
Yes, you should be able to do the same, carry out the similar procedure with solo high. Yeah, it should work. It should work very similarly. Yeah, because as long as you understand the coordinate frame that you're in, all this reprojection machinery works the same way. Yeah. Okay. Yep. So,
I'm not exactly sure what the last question was, but maybe it's similar. This combining of the pixels like into one image to show farther into the heliosphere. Is that only with this instrument, or like you said, all these reprojections are similar to any instrument regardless?
right. Yeah. So this reprojection machinery, it only hinges on like you having a way to translate from your world coordinates to your pixel coordinates. If you have that, all this sort of works the same. So this is using an AstroPy affiliated package called reproject, and so it's generic to anything with the WCS. You just have to be able to do that mapping from one pixel grid to another. And if you have the WCS, you can do that.
Okay.
Yeah.
And one more question. Earlier you showed the sticks and the soar. So are those two kind of like clients to enable Fido to do some functionality that Fido itself can do?
Yes, yeah, that's correct. So out of the box, SunPy does not search the SOAR or the Sticks data center, but those two packages provide clients that augment Fido to do that search. Yeah.
Got it. And I'm guessing there must be more such clients, and where can we find or the utility of these kind of clients there?
Right. So that is a great question. One way that we're trying to do this is through SunPy affiliated packages. So if you go to sunpy.org, there's an affiliated package tab, I believe, that lists SticksPy is actually not on there because it's not yet an affiliated package, but the SunPy SOAR is. So I guess there is no like curated list of every single client that's been written, because anyone can write like a Fido client for anything, basically for any sort of data source. But the ones that are more kind of, I guess, officially supported, we would want to bring in as affiliated packages, or in some cases add them to the SunPy core package itself. Yep.
Okay, well, thanks, Will. That was awesome. A tough act to follow. Okay, so first thing I'm going to do is close this notebook because our memory usage is creeping up. I don't want to run out middle. I'm also going to shut down the kernels. Let's see. And then we're going to navigate to the PySpeedas tutorial notebooks. And we'll use the ones that have had the output scrubbed. And the first one I'm going to look at today is this one, the MMS Themis and ERG orbits. All right. And then the first thing I'm going to do here is just to make sure we had a bit of a version conflict as we were setting up the Helio cloud. So I just want to make sure we've got a matplotlib version that's compatible with PySpeedas. And then we'll set, let's see, and then we'll set the Speedas data dir like we've been doing, and we're going to be using the cached data in the Scratch space. So what we're going to do here is sort of like Will showed for the solar orbiting instruments, we're going to do the same thing for Earth orbit and sort of see where some of our assets are and what use we can make out of them. So we're going to set a time range for just March 24th of the event we're studying. And so the first thing we're going to do is load Themis data. And I think I demonstrated that a few times in the other tutorial. So that comes from the themis.state data set. We're going to load all 3 probes for the day-long time range. And we'll plot them. And so there are the Themis orbits. And then we'll do the same for MMS. Yeah, if you get prompted for a username, just hit enter, and we'll just use the public data sets. So this is in the MMS load state. I think that's a synonym for PySpeedas.mms.state. And then here we have the MMS orbits. Now the MMS orbit data from that call comes out in ECI coordinates, which is pretty much the same as you also see that referred to as GEI. We want to plot everything in the same coordinate system. So we're going to transform these to GSE coordinates. And we're going to use a routine called MMSQ cotrans that uses some quaternions that are provided by the MMS mission ephemeris and coordinates data set. And quaternions, you can think of them as sort of they work like rotation matrices. It's a way to represent a transformation, like a rotation from one coordinate system into another, and it can be a little more efficient than rotation matrices. And I think so. We're going to use a routine called MMSQ cotrans to do that transform using their quaternions. And speaking of interoperability, I think we're actually using SunPy to implement MMSQ cotrans. So let's see. Okay, so I haven't actually loaded those orbits yet, or maybe I just repeated that cell. So here we are, we're going to do the transform. And so we've plotted these and we can see that they're now in GSE coordinates. And then we'll do the same for the Arase probe, also called ERG. That's one that's operated by JAXA, has some similar instrument complement on it. And this comes from the erg.orb data set, the orbits. And there we are. So we can see that ERG is in, looks like about an 8-hour orbit. So it's in quite a bit closer than Themis and MMS probes. So we want to see also where these spacecraft are with respect to the magnetopause. So PySpeedas has a routine to compute the magnetopause position, actually a couple of them. We're going to use the T96 magnetopause model. And for that, we need a solar wind parameter, the dynamic pressure. And as I showed in the tutorial the other day, we can get that from the Omni data set. So we'll load that all and plot the pressure. So there you can see the early part of the day, it's kind of spiky. We have some pressure spikes, and that's going to do interesting things to the magnetopause boundary. So I'm going to move through this kind of quickly because we're a little short of time, but I think we're probably going to still go over a bit. Sorry. Let's see. So one of the inputs, this T96 routine takes, you can pass it spacecraft positions this works in GSM coordinates, and it gives the outputs in GSM coordinates. So I'm going to do the cotrans first, and then plot the GSE and GSM coordinates. And then I'm going to, pull, this routine takes array inputs. It doesn't take t-plot variables. So I have to pull the position data out of the t-plot variable. And then things we need to convert to Earth radii instead of kilometers. And then we're going to call this MPOS T96 routine. And then it returns several things. The ones we're only interested in the X, Y, and Z of the magnetopause. And this is just, it doesn't give you like the whole three-dimensional shape. It's just going to be 90 points on the boundary. And I think it's maybe in like the GSM XY plane. So then we are going to just randomly pick a timestamp just for the sake of converting the magnetopause positions back to GSE so we can plot everything in the same coordinates. So let's just go ahead and do all this. I don't think I need to belabor this too much. Now we're ready to make the orbit plots. And this is going to be another example where we're going to take the t-plot variables apart. We don't have anything in PyTplot yet to do nice orbit plots. So we're just going to pull the positions out of the various t-plot variables, and we're going to plot them in Matplotlib directly. We're going to take these 3-dimensional positions, and we're going to project them down onto some 2D planes so you can visualize them. So we're going to set a plot size. This little section of code, we're just going to get a nice graphic of the Earth that we could put at the center of our plot. So that we have to find that in the MMS directory from wherever it's installed on your system. And then we're going to set up the 3 Matplotlib plots. So XY, XZ, and YZ planes. And we're just sort of setting up the limits and labels and so forth. We're going to plot everything in Earth radii. So we have a convenience routine in PyTplot, TKM to RE, that can do that conversion either way. So we're going to apply that to the Themis state variables that we saved and the MMS state variables. We don't have to do anything with ERG because those positions are already coming out in units of Earth radii. And then we're going to make a list of things to plot. So we're going to add, so we need just a list of variable names, and we're also going to plot each group of probes in a different color. So we also need a list of colors. So here we take the Themis state variables, add them to our list, and we're going to color all 5 of those red. And then we're going to do with MMS, we have 4 variables. We're going to color those all blue. And then ERG is just a single probe. We're going to color that green. And then here, we're going to go through that list. We're going to pull out the data values, the coordinate positions. And so we're going to plot these on each of the axes. So on XY axis, we're going to plot the 0th and 1st coordinates, X and Y. For X and Z, we'll plot components 0 and 2. For YZ, we'll plot components 1 and 2. And then we'll use the appropriate color. We'll set some plot labels. We'll also plot the magnetopause positions that we've transformed to GSE. And then we'll place a legend, and let's see what we get. So this is in the XY plane. This is sort of looking from the side in the XZ plane, and this is looking from like the sun out. Whoops. So let's look at the XZ plane. So you can see this out here, 2 of the Themis probes actually orbit the moon. So they are hanging out way out here. And it's kind of a pity. It looks like everything has their apogee oriented towards the day side. Sort of the jackpot would have been if we had the apogees back in the tail, because it's the processes, the reconnection happening out in the tail is what's driving the auroral displays that we had to look at the other day that we're studying. But there's interesting stuff going on the day side too. So that's what we're going to look at. So first, I want to call your attention to these 2 magnetopause models. So I think I sort of glossed over this, but we calculated that boundary for 2 different dynamic pressures. The 3 nanopascals is more of a typical value, and we saw it spike as high as 14 nanopascals. So that's plotted in the solid. So you can see what that does. It pushes that magnetopause boundary in towards the Earth and sort of compresses it. And so we can see that we have Themis and MMS passing through that region. And so the next couple of notebooks, we're going to look at what was going on in MMS. Questions so far? Okay. So next, notebook I'm going to look at is the MMS summary plots. And this one, this took a lot of memory. And so we decided just to avoid, the risk of crashing the Helio cloud for everybody. I'm just going to include these as static images in this notebook. I do have the commands in here that generated it. I just want to scroll down. Let's see. Yeah, so I have this commented out, but it is literally just one PySpeed-S command that can generate an MMS overview plot for the entire day. And we're just going to look at probe 1 here. And so I'm going to scroll down. Again, the MMS CDFs, I have a few issues with the metadata, but nothing that's going to stop it from running. And so here's our overview plot. So this is for the whole day. You can see that the perigee is here. So we're going to look at the inbound leg, the early part of the day. These panels here are spectrograms from some of the particle instruments. So I think we have electrons, ions, and then electrons and these two are, okay, the top two I think are ions and the bottom two are electrons. We're particularly interested in like this area, if you can see my cursor, where we're actually crossing the magnetopause. I'll show you a few things. You can see the density here. The proton density is sort of jumping up here, and then it goes back down and sort of going back and forth here. Same thing with densities computed from a different instrument. Let's see. So we're going to need to zoom in on this. So I'm going to come down. I've also loaded some Omni data because we're going to look at some of that. So here, I've used pytplot.timespan to set a start time of 1 hour UTC, and we'll just look at 8 hours. And then we're going to look at some AE index data, the flow speed, proton density, and pressure from Omni, and then magnetometer data, bulk velocities, and densities from MMS. So here is the plot we get from that. So this is a little closer view. So what's happening here is we're going in and out of the magnetopause. So out here, we're in the solar wind. You can see the very high velocities. We cross the bow shock here at about 2 hours. So you can see the particle velocities go way down, density goes up. And then what happens here between 3 and 4? Well, that is when we start seeing the pressure increase in the solar wind. And so that is actually, satellites here. Solar wind has blown the bow shock past the satellite. So we're back out in the solar wind in this section. And then you can see the solar wind has the pressure has a little bit of a decrease. And we find ourselves back in the magnetopause for a little bit. And then we go back out in the solar wind for a little bit. And then here we are in the magnetosheath. We're past the bow shock. And then you can see this little glitch here. It was very interesting, where we have the magnetic field sort of changing polarity. And then we also have an increase in the particle flow speeds. And that also looks like it changes direction. And that is, that's a signature of a magnetic reconnection. And so when that happens on the day side, and correct me if I'm getting the science wrong here, I'm not a heliophysicist, the reconnection on the day side is what lets the particles into the magnetosphere, and then reconnections out in the tail are what drive them back towards Earth, causing the aurora. Yeah, so that's all I want to show for the summary plot. Now, there are two more things I want to show. I want to take a closer look at the particle velocity, or the particle distributions, I should say. And this is the generate 2D slices in MMS. And I'm officially over time. But let's see how much of this I can get through. So yeah, we're going to take a closer look at those ion flows around the time of that suspected reconnection event. And I'm going to use something called MMS part slice 2D. Now, why we're doing this, we already saw the bulk velocity, but that doesn't tell the whole story. Sometimes you really need to look at the three-dimensional distribution of the particle energies. Like in theory, you could have like a beam coming this way, a beam coming this way, and they would sort of average out. You get a bulk velocity of 0. So just looking at the bulk velocity doesn't tell you the whole story. What we could do is take this 3D particle distribution. So two of those dimensions are like the sky coordinates you're looking at, in the azimuth and elevation angles. And then at that chunk of the sky, you're resolving different energies, which correspond to different particle velocities coming from that part of the sky. And what we can do is we can take that 3D distribution and make it a little easier to visualize by taking slices through it at different coordinate planes. And then, so we can look at the velocities, coming from multiple spatial directions at once. So that's what these slice 2D parts are. So let's go through some of these. We picked a time coinciding with around the time when we saw those magnetic field and ion velocity flow reversals. So we're going to look at ions from the FPI instrument. We're going to take a 2D slice. We're going to specify that the species is ions. We're going to take the particular slice we're going to look at has the magnetic field direction on one axis, and then the plane is sort of defined, I think, by the bulk velocity. So I think we're taking maybe a perpendicular cut through it. And we're going to specify an energy range of 0 to 20,000 electron volts, I think, is the units. So let's do that. So this takes a little bit of time to load that data. Ignore those warnings. And there we have the slice. So we use the geometric interpolation method here. So you're seeing like the actual bin boundaries of the angular bins and the energy bins sort of radiating out for this instrument. So it's a little chunky. It's maybe a little hard to interpret. Let's see, I'm going to skip this part. You can get the slice data structure itself, which is a dictionary, and you can look at some attributes of it. I'm just going to blow through that since we're short of time. But a little nicer plot is if we generate the slice with 2D interpolation. Let's see. So here we've just plotted like a 1D path through one of these two-dimensional slices. But let's look here. This will generate, I think, a little bit nicer plot. So here we are. So the x-axis, which is the magnetic field direction, is here. So as we radiate out from the origin, we're looking at larger and larger velocities in the different directions. So you can see, so this is in units of kilometers per second. And you can see, it looks like we've got a pretty nice beam here, a nice coherent structure with, that's moving like about, well, let's call that 400 kilometers a second. So for inside the magnetosphere, that's a pretty fast flow. So what we think is going on here is, so you have this plasma coming in, the CME that has its own magnetic field, and then we have the Earth's magnetosphere. And so these two magnetic domains are sort of colliding and compressing and building up energy in the magnetic fields. And so at a reconnection event, the fields sort of reconfigure themselves, and that magnetic energy gets put into the charged particles, and they get blasted out of the area. And so that's why we're seeing these fast ion flows in this region. So I think just for the sake of time, I'm going to stop there with the particle distributions. And the last thing I'm going to show is this card that changes. We're going to look at this last notebook, Finding Magnetic Nulls, which is something, this is why I chose MMS data for this demo. MMS is a 4 spacecraft in a sort of roughly tetrahedral formation. And when you, like, if you only had 3 spacecraft, if you think of how, if you want to characterize what the magnetic field looks like in that area, well, 3 points form a plane. And so what's happening outside, like perpendicular to that plane, you can't really say anything about that with only 3 probes. But if you have a tetrahedron, you have spatial information in all 3 dimensions about how the magnetic field is varying in that region. And that lets you do something very interesting, which is locate magnetic null points. Those null points are where the reconnection happens. And what we can do is, if we have that, field measurements at 4 points, you can estimate the gradients in 3 dimensions, like how each of those magnetic components is varying. So you have, what you end up with is like an estimate of the field at the center of the tetrahedron. And then we know how it varies in all 3 dimensions and in all 3 components of the magnetic field. So that gives you a 3x3, what we call the Jacobian matrix. It's basically like you're estimating the first derivative of the magnetic field in that region. And if you have that, you can sort of invert that and find out where all 3 field components are equal to 0. And that's a magnetic null point. So, we have code in SpeedAsk to do this. This actually came from a question that was posted on the PyHC Slack. Somebody was interested in looking at magnetic null points with spacecraft. And I was kind of surprised to see that we did have that. So, so thanks, Nick, for posting that to the Slack. That was inspiring. Okay, so we've imported some PyTplot utilities. We need to know the MMS spacecraft locations. And I did load FPI data for this. Okay, we do want to work in GSE, so we'll do that coordinate transformation again. We're not done loading FPI yet, okay. So we'll just wait for that to finish loading. We're waiting for this. Yeah, I know we're running a little late, sorry. Oh, we got to cut it there? Okay. Well, that's too bad. Anyway, this notebook you can run on your own if you're interested, and we will cut it there. Sorry to not be able to show that. But any final questions before we go to break? Okay, well, thanks very much.
Hey guys, so we're on break now. We're just going to let the extra 10 minutes fall off that break here, and we're still going to come back at 10:50. So please enjoy your, I guess now 18-minute break, and we'll see you back here. And we did notice the Q&A questions on Zoom, by the way. We will have those answered very shortly.
No, lovely.
this chicken pox, so I had chicken pox as a kid, and then at any time in the future, it's a will activation. Oh, yeah, yeah. That's why people have that factor. You can show always like multiple clips. It's like a something. So I was thinking special medicine that goes down with the second one versus the yeah, actually that's a viral virus. That's a special one. Yeah, it's just it's actually off of them. So it's using that left arm. It's not first, I kind of let that off. Not move too much, so it is.
Okay, it's 10:50. So I'm going to encourage everyone to come back in and Jim to come back up and finish up the Pi speed ass portion of his presentation.
Which one of these is live? Okay. Let's see. So hi folks, it's me again. I'm not going to get rid of me that easily. Actually, Darren was very gracious to cede a few minutes of his presentation so I could finish showing this magnetic null demonstration. So when we left off, we were busily loading some data from all 4 MMS probes. So let me scroll down past all that. And we've co-transed everything to the same system. And now we'll look at a little summary plot of what we loaded so far. And so here you see the MMS1 probe position and velocity. Here now we're zoomed in and we could see a little better what's going on with the magnetic field measurements in this region and what's going on with the particle velocities and particle energies. Just to set the context, we want to get a sense of the probe separations and the orbital velocity at this time. So we're going to use PyTplot subtract to get the differences between pairs of probes. And then we use this tvec that adds the total, like square root of x squared, y squared, z squared. So we could just get the total distance in all 3 dimensions, and then we'll plot those. So these position differences were, somewhere between 50 and 75 kilometers. And our velocity of the constellation is about around 3.5 kilometers per second. So just to put things in context later, any feature that's stationary with respect to the Earth, it's going to take the MMS constellation, let's say 20 seconds or so for that to go through the tetrahedron. So now we're going to go ahead. We have all the position variables loaded. We have all the magnetic field variables loaded. And then we're going to find those magnetic nulls. So internally, what's going on, it's using this 3-dimensional information to compute the field gradients in space in that region. And then we can invert that and sort of solve a system of equations that gets us the point in space where the magnetic field, all 3 components are 0. So let's go ahead and do that. It'll take a little bit. So we're doing some smoothing internally to make the results a little more understandable. And then it's interpolating everything onto the first probe's timestamps so that we're taking, we're estimating the instantaneous magnetic fields at the first probes or at all the probe positions at the same times. And okay. So I think that's done. And now this routine returns a whole bunch of t-plot variables, some diagnostic quantities. So I'm just going to jump in and start plotting some stuff. So we're going to look at a 60-second slice of data. And as you'll see, it gets pretty chaotic. So we want to be looking at some fairly short time intervals. Let's see why. Okay. So here's a 60-second slice, and you could see like towards the tail end of that, you see all the fields sort of getting close to zero, and that happens possibly at a few places. These are so this method, if the magnetic field measurements differ at all, it's going to find a null. So we may or may not believe that detection, depending on how close it is to the constellation and some other figures of merit. But let me just go ahead and zoom in on a closer time interval. So here we're starting to see things happening. And this next to the last plot is the most interesting. So this is, we have the distance of the null detected from the constellation. So you can see these are on the order of 0 to 100 kilometers. So that seems kind of plausible. And then this bottom panel, we have a couple of figures of merit telling us how reliable we think that null detection is, and then how reliable are we characterizing the topological type of that null. So these come in a lot of different flavors. You could have type A or type B. I'm not an expert. I don't necessarily know what all of these mean, but they can also be radial nulls where you have sort of field line converging to the null point, or they could be spiral nulls where the field lines are kind of swirling around it. And then some of them can sort of simplify to a more two-dimensional type, like an X type or an O type null. And this characterization, this comes from the eigenvalues of the Jacobian matrix. So you get, it's a 3x3 matrix. So you get you're solving a cubic polynomial to get the roots. And so possibilities are that all three roots are real, and that corresponds to like one class of nulls. And then some of the other types, you end up with two of the eigenvalues are complex conjugates of each other. And that's like a little bit more complicated of a topology. So we've overplotted the distances with symbols showing what kind of null we think that is. So we're going to zoom in even a little closer. Even closer, maybe. Yeah, so we're zoomed in here on just a 5-second interval. And we can see it looks like we're detecting many null points. This reconnection process is not just something that happens at one point. It's happening sort of throughout this whole area. And you can see that we're detecting different types of nulls. And remember we said it takes about maybe 15 seconds for the tetrahedron to pass by a stationary feature. We could see these things are coming and going much faster than that. So two things are happening. These nulls are forming and disappearing on kind of short time scales. And sometimes they could get sort of pulled along with the local particle flow. So some of this activity is sort of flowing past the spacecraft faster than the spacecraft are moving through space. Now looking at these figures of merit, we want these to be below about 0.4. So like this region here between 21 and 22 seconds is kind of interesting. So it looks like here we're detecting type A radial nulls, I think. Here, these would be type B spiral nulls, although we're maybe not so sure about the quality of that detection. But anyway, if you're more versed in heliophysics and reconnection than I am, that can give you some useful information. And I think I'm just going to cut it there, and we'll bring on Darren and his presentation. So thanks very much for the extra time, and thank you all for bearing with me.
Thanks, Jim. All right. Next up, we have the PySat and Komodo combo. Were there
right.
any remaining questions for Jim before they get started? Okay, cool.
Okay. Can you hear me all right? So I'm going to close this. I will shut down the kernels here and back up to the ITM PySat Komodo directory and open the notebook. All right, so we're looking at the same event here, trying to look at it from a sort of lower altitude ITM perspective. So we're going to be looking at timed SABRE data of the temperature and comparing that to some model data. So first we'll do all of our normal imports here. Got to get some date time, matplotlib. So we're going to be using the PySat NASA ecosystem package from PySat. And I'll be using PySat space weather just to get some space weather indices out to sort of look at what the geomagnetic activity looks like at this time. Here's all the Komodo imports. We'll be sort of, Darren will be getting some data from SSC Web for the timed orbit and then flying that through a model, and we'll be comparing some plasma temperatures. So on those imports, and then this is, you won't need to do this ever really on your own. This is just working in these notebooks, making sure that we have all of our directories pointing in the right place. We should be fine there. Register our PySat NASA instruments just in case. And I decided to pull in quite a few days here. The atmospheric response is pretty prolonged for these storms usually. So they happen over the course of a day or so. Just get these day numbers for later. So I'm going to start by getting the KP index from the space weather ecosystem package, and then I'll set up the orbit information for the SABRE instrument. So this is the platform is timed, the instrument will be SABRE, and we'll pass it that orbit information. And then we will load this data. This is going to take a little while. There's quite a few days of data. Hopefully with the kernel resets and everything, our memory usage is pretty low. Once we get all the models in, it's going to be quite a bit of data between the satellite measurements and the model. So this is one way to load multiple days. You can give it sort of the year, the day number, an end year, and an end day number. You can also just give it two date time objects as your bounds. Either way will work for loading multiple days of data at once. And you can give it specific times, and it'll only load in, a subset of the data, regardless of the model, or sorry, regardless of how the data files are actually organized. We just got this warning here. There's no cleaning routines available for SABRE. That's all right. We'll just use the uncleaned data. A little information just to make sure we're looking at something. I'm actually not that familiar with the timed SABRE data, so I put this in here so that I can look at what all the variables are and get a better idea of what I'm looking for. I knew I wanted to look for temperature, so I'm looking through here for some temperature, and I notice there's multiple like latitude, longitude, altitude values. There's this TP latitude, and then there's SC latitude, and I'll describe a little bit about what that is in a minute. Then we have this K temp, so it's just temperature in Kelvin, and that's mostly what we'll be looking at. So we'll set up a little plot here. I just want to look at the sort of where the spacecraft is, what I should be expecting from the data. So I'll be looking at the spacecraft's average altitude, this TP altitude. The TP is tangent point, and then the spacecraft latitude. Just get these plots. So we've got, pretty narrow altitude band for the spacecraft at around 600 kilometers, but then the tangent point altitude is much lower, around 140. We've got an inclination of about 50 degrees here. So what's the tangent point versus the spacecraft altitude? So the spacecraft has its orbit at around 600 kilometers, and then the SABRE instrument is an imager, so it's scanning the limb of the atmosphere, and so it's getting measurements from about 200 kilometers down for plasma density, temperature, and things like that. So if we're interested in comparing these measurements to the model, we need to know where the measurements actually represent. So we're going to be looking at the tangent point coordinates for comparison to the model. So first, I'll just look at what the temperatures look like for this time range. So I'm looking at the, wait, is this neutral density? That's not what I wanted to look at. Well, I'm looking at density instead. So this lower plot is the KP index. We can see that around March 23rd, we start to see this increase in geomagnetic activity in the ionosphere, and it lasts for about a day before falling off kind of slowly. There's not any obvious response in the density, although you would expect some plasma density change during a storm, but we're only looking at about 120 kilometers and down, so we're pretty low altitude here. So now we finally will look at the temperature. We'll just do a quick plot. So I'm just grabbing the temperature in Kelvin and using the built-in plot on the pandas series for this and putting in a little label for our legend. Then I am doing a sort of rolling average here over about 240 points. It's about 4 hours-ish, just to hopefully get a better idea of the response of the ionosphere here to this storm. So around that sort of March 23rd, when the KP was increasing, we don't see a very strong response in the SABRE data, actually. There's a small increase here. So we are seeing some response, but it's not as strong as I was sort of hoping when we were looking at this data. But we're going to move along and sort of see what the model response is to this event and look through that with Komodo. Yeah, okay.
All right. So let's go on to the next step. So from Komodo's perspective, we've got all these data sitting in the pandas arrays that we just got here. So let's just kind of take a look at it and see what's in there. So I'm going to look at this TP altitude variable and look at its shape and look at and print some of these values and see. We've got an array that's 5714 by 400. And so that basically means this data set, there's 5,700 and some times and 400 different channels that it's looking at. So when it's looking at the limb, it's measuring across a perspective on that line, and they're all at a little bit different altitude, okay? So again, it's a pandas, so what's packed in there, and so there's time is packed into there. So at the first point, this is the value that I got out of here for the altitude, and time is packed in there and a few other things. So, okay, we understand what's in that data set. So let's actually take this and copy it over to Komodo. And so Komodo has this, so where I loaded up the very top is a functionalized data set library. So it's just called FD right here. And And so if I make this little dictionary and says, hey, here's time has this ranges, and Komodo works with hours from the first day of data. And so there's 4 days of data here. And there's 400 channels. And so those will be my 2 dimensions here, time by channel, which matches my array size above. And I'm going to load in altitude, lon, lat, and temperature and load that into Komodo. So now I've got this in Komodo, and I've got these variables now as a function of time and channel, and their units in an example, okay? So now I have this variable, I can define the altitude that I've loaded up here, and I can call the built-in Komodo plotting and just pick one channel. I picked 137 and say, what is the altitude in channel 137? And you look at this and say, wow, that has a fair bit of variability. It's around 107 kilometers, but it goes from below 106 to above 108, right? And, I can zoom in on this a little bit and say, wow, that jumps around a little bit. If I'm going to be comparing with a model, I prefer to pick an altitude and then fly that altitude through the model and look at it. And so what can we do to get a smoother altitude profile through this? So the first thing I want to do is again, this plot is shown in hours. It's not a big deal, but we can do a little conversion and just take this, because when I'm using Plotly, I can just pull out the x-axis values, convert them to date times, and redisplay the image. And now I've got the same plot with nicer axes across the bottom here. So that's just fully customizable that we can add on later. So we can do this analysis for a specific channel, right? But as I showed it, it varies quite a bit. So let's try to actually extract something at 107, okay? So I don't happen to have a function sitting around that does that. And so I just sat down and wrote one by hand, okay? And this is not the cleanest or perfect code, but this gets me my interpolations. And so what this is doing is it's building a couple of arrays, which is finding, so for at every time, it's going to find the 2 indices that bracket that altitude, and then it's going to compute the weight factor of those 2 indices. And so basically what this is going to do is say for every time, I can just drop in a quick little function, and I'll get the interpolation of any of my values at exactly the position I want, okay? And so it's just a simple thing, and it's finding the closest point here. So I've created these MF and MI little variables here. So now I'm going to dump the Sabre data, the values. I'm going to dump it into a straight array, not a pandas array anymore. And I'm going to create some new arrays that I'm going to actually interpolate into. As I'm going to fly through each time and say my altitude is now this little function of my indice matching and my weight factor matching. And so I'm going to now interpolate everything to 107 kilometers for those values, okay? So that runs pretty quick. So that got me the values. But now, as was mentioned, I think it was yesterday talking about time is always a crazy thing to work with. And it turns out that this Sabre data is in date time 64, which is a date time reference that doesn't have a set reference point to it, right? And so it's not like date time itself, which always has a certain fixed reference point. And so you can't just call put a dot timestamp on the end of a date time 64. It doesn't know what the reference point is. So you got to do this little complicated step of taking the time I've got in Sabre, subtracting what the timestamp reference point is, dividing by a second, and you'll actually get a timestamp out of that. Then you can take that timestamp and convert it back into a date timer array of date times. Okay, so that little step is necessary. Now in Komodo, we'd like to work from plus or minus 180 in longitude, not 0 to 360. So we'll do a quick little fix on that and shift things around. And so now I've extracted this data right along these points. Now I'm going to save this to a little file right now for now, because I'm going to use this again in just a little bit. So I'm just going to dump these values that I've calculated, this time, lon, lat, et cetera, into a file. And so my file now looks like this. It's just a simple little text file with the timestamp and my 3 coordinate positions. And I'll explain why I did that in a second. So now the same data I can go back and do the functionalization of data again, where I drop in these new values. So I dropped in the time, out, lon, lat, density, temperature, drop those into and commodify those. Now I've got these variables, which I can do full interpolations in space and time to look at. And so just do a quick plot of that and make sure that I got what I wanted out of this. So if you look at all these values, this solid blue line here is the altitude. And you can see that, yes, the altitude is set at exactly 107 across this whole thing. And then you can see that when I interpolate to those points, I interpolated all the other values follow a nice smooth path as well. And then this is the temperature and how it varies throughout this. And so my interpolation seems to have done what I wanted it to do. Okay, so we've done that. So now let's go and look at a model. Okay, and so because the time satellite was flying around 600 kilometers, I'm like, oh, well, let's just find a model that I've got to run at the CCMC that covers that range at about 600 kilometers. Not realizing at the time that, oh, the Sabre is a limb scanner and the data is actually at a much lower altitude. So we're actually going to have model and data that have a very small layer of overlap. The data goes up to around 120 to 140 kilometers measured from Sabre. The simulation starts at 90 kilometers and goes up to 1,000. All right, so we've got a window of overlap here. So I'm going to read this model. This is now stored in the scratch space on the cloud here, and I'm going to read in the neutral temperature, reading in the density as well, but I'm not going to be using that for right now. So I'm setting those variables, and I guess the first thing I want to just look at and say, well, what density and temperatures are in that file? And so there are these various density variables. Some of them are species, et cetera, and a few temperatures. And I'm just going to grab the neutral temperature variable here that I had set and grab that one, which is, it tells you what its coordinate system is, what it's a function of, what its units, all that metadata is there available. Okay, so now I'm going to load that run output into Komodo. And now I've got a list of variables that I've got available. Now, again, as I had some of my other examples yesterday, the TIEGCM model operates on a pressure level grid. And so the altitude is actually pressure level. So you have to invert that and get an altitude in kilometers out of that as well. And so there's a few extra pressure to height conversion variables that are in here. But then I've read in my temperatures and densities for those. So we'll look at this. This is just saying this is the base time for the data. So I've read in a data that starts on the 19th. And so that matches up with the data that we've pulled in as well. And I'm going to generate a plot. Now this is going to take just a little bit because this is actually a fairly high resolution output. And so there's a lot of data there. And so it's actually loading the necessary files, doing some impromptu pressure level conversions, and it's going to generate a plot. All right. And this is going to take up to about a minute or so, and it's going to make a plot. So I'm using the base plot object where I'm just asking for the neutral temperature here. I've picked hour 74 for this particular one, and the height again is this 107 kilometers that we had from before. So this is going to generate a plot that covers the whole sphere at that altitude at this particular time. And this is taking a while today. Let this crunch for a bit. Not too loaded on memory. It's just taking a little while here on this. And then this other plot here down, the next one down below, we can skip that one for now because it'll take almost as long as the first one. But we have a little function that actually makes plots more specific for scientists that wanted to use this data. And so in this particular example, we're doing plots that add the shoreline. You can choose your coordinate system, so it'll do a coordinate system transformation if you want to, and do a lot of other fancy items with this. And so that will generate a plot in a little bit. This is taking quite a long time. I'll start talking about the next section while that generates a plot. And when it finishes, I'll jump back and show that. So now one of the things that Komodo has as an object is we can fly things through it. And so if we set a trajectory, you can actually fly that through the simulation output and extract that. And we have various methods of doing that. We can fly a real satellite. So it'll actually, we have a tool that actually uses HAPI to go to SSC Web to grab the satellite trajectory and whatever coordinate system you want, pull it back and fly that through a simulation. We can do it through, you can make virtual satellite trajectories, or you can fly through your own custom positions. And so that's what I actually created up above, was that little file which says, I want to fly those positions through. It's not where the satellite was, but it's where the satellite was looking and where it saw 107 kilometers. And so I'm going to take those points. And so I'm going to set a few variables for time for when I'm starting and stopping. This first block here where I say don't execute, this is actually the code you would use if you wanted to fly the actual satellite position through it. And so you name the satellite as timed. You say what you want to output some results from, and then you execute real flight. And real flight will actually pull in the start and stop times, what model you're flying it through, the name of your satellite, and it'll go through and do all of that, and then you can drop it back into a functionalize into Komodo and make your plots. Okay, and so we're not going to do that one. But what we will do is use this extraction path file that I saved a few minutes earlier here. And so we're going to actually take that value at 107 kilometers, save it to a file, and we're going to call my flight, which is not the real flight, it's my custom trajectory through the flight extraction. So we're going to send that file at it through this model and where the model output is sitting, and functionalize that. Now let's see if my plot has ever finished up here. It is not. That is crazy. I might have to just stop this kernel and go back and skip that. That is taking a really long time. Demonstrator effect. I probably did this about 15 times over the last week, and it never took this long. All right. So we're going to go and restart the kernel. And I'm going to jump to the top and re-execute the top cells and skip when I get to that one, because these all went pretty quickly. Okay, that one and that one. Now this should be here pretty quick. Catch up. Yeah, where is this hanging up now?
Probably on the load.
Oh, the load takes a little bit, yes. Okay. So this is going to fly through and catch up to me here in a second, and then we'll just go ahead and skip these two cells and jump down to here. Right there, that's going. There we go. Well, that one worked. All right, that's flying through. Okay. There's that. Okay. Got my variables. Now, I skipped those two cells. Now I'm going to go down to here. Load those variables. I would have skipped these two here, and now I'm going to actually do my fly through. Okay. Now that's going to take a little bit of time too, but not as long as the plot takes. So what this is actually doing is it's actually taking my 4 days of simulation output, and it's reading, so it's reading the path that I've set forth, those 5,700 and some times, and then it's reading the appropriate files as a time, and it's doing time interpolations in time and space all the way through as it does its fly through. Okay, and so it's reading the netcdf files that are the output from the model, and it's crunching through that. So this will take just a bit too. Why is this? And when then that is done, we will actually use the default plotting option in Komodo to actually see what we've got. All right. This should be the last slow cell to run. After that, it's a little more straightforward. Do, 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 do.
So I have a question about the Komodo data output. When we have this simulated fly through of the model, I don't know how to do any processing on the Komodo object that comes out. Does it have like a built-in rolling average type function, or do you need to pass that through to something else that does that?
So there's not a rolling average built into Komodo right now. It's certainly something we could add. It's not been something that anyone's asked for before. A little bit down here, I wrote a little 5-line hack that kind of does a rolling average that can kind of simulate that a little bit. But it does it by so you've made this plotly figure object, which has all the data in it. And I can go through and I can take a line of data and average things out and throw it back in as another trace in the plot. And I'll do that here in a little bit. All right, this is demonstrator day being really, really slow. Okay.
There we go.
Hey, there's another line that came.
Oh. How many times will it invert the pressure level grid?
It does not need to do it for all the times. There's
Okay.
a couple of these, so. But you can see the memory is climbing as it works through this. So again, I'll kind of keep talking down below. So this is going to make a plot that's going to show the temperature. And the temperature is going to look similar to what was shown for the Sabre data itself within their own tool. And so I can take, so I've already made a couple of Komodo objects. I Komodified the data at a channel 137. I Komodified the data interpolated to 107 kilometers. And now I've made a Komodo object for the model, for this fly through the model. I've Komodified the model, but now I'm going to Komodify the output of that slice. I've got 4 different Komodo objects already floating around in this notebook. But they can be added together and combined with each other really easily. And so I'm gonna actually take them and say, okay, here's my Komodo object from above, and I'm gonna grab the temperature and make a little figure object from that. I'm gonna adjust the dates in that figure, and then I'm gonna use this add trace. I'm gonna take this figure that will be showing up shortly here, the temperature along the extraction through the model, and I'm going to add the values that were actually observed at that position as well. So I can just add those 2 plot slices together. Okay. Now just have to keep moving on here, I guess. So this is my little hack routine that I wrote to do some of this averaging stuff. Okay. So I just called it half resolution. And so it's going to take a figure that I give it. I'm going to take that figure. I'm going to pull the X and Y values out of that figure. And then I'm going to go through and basically average them. So every pair of points, I'm going to pull together and I'm going to give it the average of the two times and the average of the two values. And you know, for average, you can always just do a value plus a value divided by 2, right? That will always work, except that doesn't work for date times. So this little trick is to say, this is a date time, but if I add a date time minus another date time divided by 2, that actually gets you the average date time between those two date times. So it's a little hack to get an average of 2 date times. Hey, this is finally finished there. Okay, so here's my plot. So this is now a plot of the temperature through the model. And so you see a little bit bigger response from the model than you saw from the data. But again, it has a high degree of variability to it, right? So I'm going to go here and I'm going to make this combined plot. And this is now the data and the model output on top of each other. And you see it's kind of a mess, right? There's a lot of noise and a lot of variability there. So when I talked about making this little averaging function, okay, and then I can run this little half resolution thing on the figure and display the figure. And what this actually did was I actually just added another character to the end of the thing. So this is the original temperature, and then I've now averaged it by a factor of 2. But I can run this cell 3 times in a row, and now I've got the temperature. I've got the temperature averaged over 2, a temperature over 4, and I'm going to do one more time over 8. And I'm going to now zoom in on a block of this, and I'm going to turn off the actual temperature, the averaged by 2, and the averaged by 4. And now, at least if you zoom in on this, they're kind of in the same frequency range of variability, but they really, all you can say is they're in the same ballpark. They're both floating between 220 and 260, right? And they're not showing a huge impact here. So I sat down with a science expert on the SABRE data last Friday and said, hey, can you look at this and see, you know, if I'm doing something wrong, or can you explain this? And he says, well, for this particular storm, the impact from that storm probably only pushes down to about 150 kilometers. Unfortunately, SABRE doesn't measure anything above that, in that range, right? They're measuring up to about 120 to 100, maybe 40 at times. And so they're actually, he's like, I wouldn't expect to see a huge impact. You see a little bit, you're on the edge of where it can push to, but not a lot, okay? So this is not a science problem that we're working with, that we're saying, hey, this is this great result we got out of it. We're showing that we can talk these two together, but we're not actually seeing an amazing, you know, science thing out of this. But I want to show you a couple other things. So we have an extra little tool in Komodo called SatPlot4D, which we often use to look at these satellite extractions and try to get a little more context for them. And so I'm going to do this first one, and it's going to take the data that I've extracted and now plot it on a LonLat grid in geographic coordinates. So these are the temperature measurements that were observed. And you can see, based on the orbit, it's missing a lot of the northern pole, but it gets close to the south pole in its orbit. But there's no obvious area that says, oh, hey, this area always gets hotter, this area is always cooler. It's kind of a mix, right? And so that didn't really tell me a lot, but you could look at that and see. So let's look at the next one. I can take this same data, instead of plotting it in longitude, latitude, I'm going to plot it in local time. And you can see that time SABRE is in an orbit that says, I'm looking at a specific local time over and over and over where it's flying, right? And so it's very much grouped, and you can see where it's looking. But now I can do another one. I can look at it now in 3D and get a little bit better context for what's going on here. Let's take a little bit more. And there's a few options I can set here. So this is a 3D plot. I can tell it, you know, the data came in GDZ, which is basically a geographic spherical. It's a special coordinate system. I'm going to plot it now in GSE. And when I plot it in GSE, I can actually see where things are at. If I take this sphere here, and you can see this is where the orbits are flying. Okay. And so in this condition here, the x plus 1 is the sun direction. So you can actually see where that's flying. And there's a whole host of options I can set here. I can actually, if I turn this on, I can actually have the body be Earth at one particular time. Well, actually, body Earth won't work when it's in GSC. I've got to be in geographic. So that's going to probably turn that off and show it black anyway. Yeah, so it turned the body off completely. Now let's go in geographic coordinates. Machine is really slow today. Here we go. So here's now in geographic, and you can see the orbits are covering, as we saw above when we looked at where it covered in lat long and geographic, it covered almost everything, right? And you can tell from the very faint lines along here that it's missing the polar cap above, but it's flying quite close. And scroll down. There we go. Quite close to the southern pole and see where that's flying. And then we can do a variety of other things. So I'm going to go here and go back, and I'm going to turn. I'll leave that on. It's all right. And this is actually set up. I've broken up the flight into orbits, and so I could actually play this as a movie, and you can actually watch the progression of the orbits as it goes around. So this is a visualization available that Komodo provides using Plotly to jump through here. And I can play this, I can pause it, I can jump to a specific orbit that I want to look at. And I've chosen here to break the orbits by when they cross the equator. I can do different groupings of data as well on here. So this is just ways to, again, analyze your output and try to give yourself some context for what you're looking at. But what we found again with this simulation was, our data model was just, yes, they agree in the ballpark of where their temperatures are going. So these models are doing okay, but they're not a great correlation and a one-to-one match for where they're going. So.
Yeah. And their response to the storm is pretty different.
Yes, yeah. There's with the model actually seeing the storm at the higher altitude, it actually can push a little of those effects a little bit lower than what the observed data was actually seeing. So, are there any questions on what we were doing or other things that we could be doing to look at these simulations? We're doing more and more in Komodo now and trying to automatically just fly a whole bunch of things through simulation output. Looking at what Jim did, I could have pulled in a whole different set of presentations that I don't have on here, obviously, to look at, again, output from a global magnetosphere model, where we can actually calculate the magnetopause in the model, compare it with these empirical models that he used, and then again, fly the satellites through them and see where they hit various boundaries, right? And so we can do that all with the tools with using Komodo, but also with the Plotly for 3D visualization to fly around and look and see this is where this one hit and this one's where it flew through. So those are extra things that we can do to try to help scientists find ways to analyze what they're working with.
Great.
All right. Anything else? I think otherwise we're done a little early.
Yeah.
don't think people will complain too much, but
Any questions for Jonathan and Darren? Okay, well, if not, we can go ahead and break early. I believe the next item is lunch. So keep to schedule and come back at the same time, so you'll just have a bit of a longer lunch. Just double checking, Sean, had there been any questions on Zoom? Oh, but of course. I don't know if everyone already has lunch plans, but if you'd be interested in going for like Mexican food on Pearl Street, come over here. Nick, do you want Mexican food on Pearl Street? Okay, they have vegan options.
Hey there for everyone in the room and anyone who is still listening online. Just wanted to let you know that we are extending this lunch break by a little bit impromptu because a large group of people went to a Mexican restaurant and then it took longer to leave than expected. So we will resume as soon as Julie and the group get back. I'll make this announcement again in just a few minutes, but also for anyone online who happens to be hearing my voice. The next thing we are doing here is the PyHC Challenge Ladder Coding Challenge game, and that is actually only for in-person participants. So if you would like to try to follow along, you are welcome to, but this portion of the evening was not intended to be done by remote participants, so feel free to sign off if you would like.
Oh, good.
All right. All right. We're going to finally go ahead and get started. Thanks for waiting. Rio Grande took forever with our checks. So next up for this afternoon, pretty much what's left is the PyHC challenge ladder. So Sean's going to explain it. We're going to do it. Money's on the line. Pay attention.
All right, testing, testing. Am I coming through? Sweet. How's that? Is that any better? Yep. All right, that should work. So, all right, hey, cool. We are going to be spending the rest of the afternoon doing a coding challenge game. This is the first time running this sort of thing. Hopefully it goes well. We had feedback before from other summer school instances that we wanted more hands-on kinds of stuff, and this was the funnest, most interesting way we could think to do this. So for the next 10 minutes here, we have a little web app that I'm going to show you how to use to walk you through how the game is going to work. And then we've got 2 hours to play the thing. So if I can remember the URL, I believe it is codingchallenge.heliocloud.org. Yep, thank you. Up right, and you're going to need to sign in and yep, same credentials, but I do not have mine committed to memory here, so give me 1 second to dig into my key store. All right. That's funny. All right, cool. So hey here, everyone. I'm going to walk you through this little web interface, and then we are actually going to have to restart this because whenever you log in here, it's going to prompt you for a team name, and then you show up here on the leaderboard. Clearly, a couple people have done this already, and we've got some tests, so I should clear that off just to make sure it's not ugly before we start the game. But so this is a coding challenge game where you are randomly given a coding challenge to complete that involves PyHC packages. It is called the PyHC challenge ladder because there are 5 difficulty rungs where challenges get progressively harder as you move up them. We are going to be grouping up into teams, like I mentioned in the morning. So hopefully a few of you have thought about which teams you would like to be in. Groups of 2 to 4 is what we're allowing here. I have a crisp. Damn thing. I've got a crisp $400 in my pocket for the winning team here, whoever makes it up to the most points. And I will point out that challenges in higher rungs are worth more points. So here in the first level where you're going to start, it's going to be very trivially simple. And the way we're going to actually be doing the coding here is inside HelioCloud. So I'm going to have people just run your Helio cloud and just like make a new notebook, just like some kind of scratch space to write some code. And as an example here, say this first challenge was setting the speed-ass data dir and import PySpeed-ass and PyT-plot. You're supposed to write a Python script that successfully sets the data dir and then imports them. So you would read this, and then in your little notebook in Helio Cloud, you would write some code that you think solves this. And when you think you have a solution, you are going to raise your hand, and I'm going to come over and grade it. And if I think you're correct, there is a submit task button that will ask for instructor approval. I will enter my super secret password that no one's going to see, and it's going to submit it. And then I will encourage people to try to move up the rungs into harder coding challenges because they are worth more points. It doubles every single time you go up, except for actually I think the second rung is worth 4 points. So that's actually quadruple the points in the first one, and it doubles thereafter. The idea of just trying to get you to move along a little bit. But if you get stuck on a task that is too hard, you have a couple options. There's a hint button at the top here that will give you a helpful hint for how to do the thing. If you just hate the task you're on and you want to skip it, you can skip it. Or if you have made it into a higher rung, you can actually click on any lower ones to go back. So I would say, as a piece of advice, 2 good ways to approach this game will be go for broke and just try to get to a really high rung and get, tons of points on one hard challenge. Or you could even hang out in the lower ones and just try to do a bunch of simpler problems to rack up some points. Hopefully that makes enough sense. Does anyone have questions on the logistics of how that would work so far? I feel like I could have explained it better. What's up? Oh yeah, just one. So like a pair programming kind of situation here. And yeah, hopefully you all, at least by this point in the summer school, know how to make a new Jupyter notebook and write some Python code. So I would say at this point, we're probably about ready to break up into groups. So yeah, Jim, what's up? Don't help him. Nope. This is officially a coding challenge with high stakes. So you can get a hint using the get hint button, but we are not going to be holding your hand any further here. Yeah. Oh yeah, that's another good thing. Anything on the internet is free game for trying to like figure out how to solve the thing. So feel free to use Google or go look at the package's GitHub repos or the documentation, or not Slack.
Can they look at Helio Cloud stuff?
Yeah, and actually the intent was to make these coding challenges pretty similar to the material you've been learning this week. So you might find useful tidbits in the notebooks that have been previously presented. Yeah, pretty much all fair game there. What's up? Yeah. Huh. Well, sorry, Pete. Now I'm putting you on the hot spot because you're the one who set up the authentication. I know my same login worked there, but I'm a data point of 1. I guess I should ask this question now. Is there anyone who has not found a team already? Because I'd be happy to help pair people up if you have not. I'm kind of seeing like team here, there. Yep, no more than 4. Got to be at least 2. I'm not seeing any hands going up, so I guess you guys figured that out. I'm glad. All right, well, sorry, bear with us for a couple more minutes. We're going to see if we can quickly figure out what's up with the authentication problem. But if not, we do have a backup version that does not have logins. So I might just give you a different URL to go to. Check back in a couple minutes. Sorry. All right, it sounds like we are quickly redeploying a version of this that does not have the authentication. So, yep, as soon as that's up, I think we'll be able to start. All right, I've heard that the fix is currently redeploying, so hopefully we'll be up in just a sec. Oh boy.
Fine points.
Yep.
Coding challenge. So I did because I saw because that one's pointing at US West too, which is the
Okay, whoops, we're resending the URL in Slack because I guess the first one was not the correct URL. Whoops.
I should have put it down or something.
Oh boy. Well, okay, here, that was a bit ugly. But I think we might be ready to start this thing. Just to go around the room really quickly, which team were you? Pleiades, all right, so your team Pleiades. What about you back there? Paige, ignore the testing one. Yeah, go ahead. It won't remove it from the leaderboard, but we can just ignore that one that's on there. Cool, so you're that one. And which team were you? Love that name. Love that name. And you guys? The aliens. Hey. Escape room. Nice. All right. All right, so boom. I am starting the timer here and I am closing this out. All right, so the game is officially on. Once you hit draw task, that'll be your first randomly assigned task. And again, just open some kind of like Scratch notebook in HelioCloud to do your solutions. And if you think you have an answer, just raise your hand and I will come over. Thank you for bearing with us. It'll be worth it for one team who walks away $400 richer. All right. We've got 1 point on the board and maybe a second point on the board coming up over here. Right. I'm also going to make a really quick announcement just because this issue was brought to my attention. Here at LASP, someone brought down the MMS server. So MMS data is currently not available. If you happen to get a task involving anything to do with MMS data, let me know and I will skip it for you without decrementing your allowed skips. Thank you. 1 minute left. Five, 4, 3, 2, 1. Time's up. Hands off the keyboards. Hands off. I'm sorry. Does anybody have a last minute solution for me to grade here? Nope. Not IDL.Pro is the winner with 138 whopping points. Good job, guys. Wow, that was exhilarating even for me. You played very well. Good job, all of you guys. Every single person got way further than we ever expected that you would, actually. We were questioning whether or not we should make all of the questions half as hard and maybe even not even have that fifth rung, but you all managed to accomplish that. So feel good about yourselves, even if you are not IDL.Pro. And all right, that is 4 of you. We do not have consolation prizes lined up. For you, and for you. Good job, guys. All round of applause to our winners. Drinks on you guys. All right, so we did have a little bit of time left in the schedule to debrief about how this went. This would be the opportunity for if you were really stuck on a question and are curious to know what the answer was, I can come show you the solution. If you have feedback on how that was, I'd be happy to hear it. This is all very informal now at this point. Yeah.
If there's something you have struggled with on any of our tackles that you could have figured out or figured out all the time, please open an issue. And say this was not clear about documentation. There's nothing as valuable as people on.
That is true. So if anyone didn't catch that, encouraging you, if you found something particularly difficult to solve, open an issue on that package and say, hey, this was super hard to use, and tell them why, and maybe the developers can act on that. I do have the solutions in front of me. Was there anything anyone wanted to see? Yes. I will actually go ahead and share my screen. Yeah. All right, so which one were you talking about there? Difference image? Is that in rung 4? Yeah. Difference image. There we go. That's this one. So the solution to the difference image The code is up here on the screen. I don't know if that's even kind of legible for you. Here, maybe I can full screen that to make that a little better. Yeah, so kind of the trick there was making that diff map and then doing the one map minus the other one. Difference image was picking two consecutive EUV images from SDO and stereo and then subtracting the two. Yeah. That was rung 4. Nothing else? Oh yeah, I can do that one. Here, let me hold on one sec. That's all the code if you want to screenshot that. Cool. And then yeah, the interpolating time one in rung 5. So we had 2 ways to do this. Starting off, we had these functions for interpolating with NumPy and interpolating with SpacePy, where SpacePy, you're using the interpol function. And then with NumPy, that right there, there's probably like other ways to do that with NumPy, but that's what we had. And then performing the first interpolation looked like this. This does not fit on one screen, so let me know if you're ready for me to scroll. Oh, convert timestamps was just a little helper function they defined up here at the top. And I was using the happy to date time function, which you guys did. Yeah. That was that part. And then, yeah. And then that was the rest of it here for into 1 hour bins. All right. Satisfactory? What's up? Yeah, which rung was that? Yes. Yep, this one right here. Oh yeah, we had changed this one temporarily, where it's the same thing but swap out space weather for NASA. It's actually very few lines of code. The tricky part there is just knowing which functions to call. Yep. So close, so close. Cool. we're at 4:36 here. Anything else? Otherwise, we might wrap up kind of early. Cool. I'm seeing thumbs up. So thank you all so much for playing.
Okay, well, we'll be back here tomorrow at 9 a.m. Tomorrow's going to be a shorter day, a half day. We'll be doing AI and ML and heliophysics and then some wrap up. And for those staying and wanting to hike, we'll be doing that after grabbing some lunch tomorrow.
I'll leave the leaderboard up for a little bit more. Oh, you want to get a picture like underneath the thing? Thank you.
My $25 thing did go through, but it already reached 400. Did you get that?
That actually ended up paying the GoFundMe fees, if that's okay with you.